So I recently uploaded a video, less than a minute, talking about the top 10 myths for experimentation and statistics. Well, I just threw it through Google's Notebook LM, and it came up with, a 7-minute audio track. So let's give it a listen.
Ever get tripped up by those so-called rules of statistics?
Oh, absolutely. It's so easy to fall into those traps,
It's like 1 minute you think you've got a handle on the data, the next you're like, wait, that doesn't make sense.
Right. And these myths,
This is
they're
not
everywhere.
real people.
They really are. So today we're doing a deep dive
AI-generated.
into 10 of these stats myths, the kind that can really mess with your insights if you're not careful.
All right, so they're
We're
doing a
gonna
deep
bust
dive
some myths
off my 1
wide
minute.
open.
Love it. Okay, myth number 10. Statistics has to be scary. I think we've all felt that way at some point.
It's funny because statistics is really just a way of making sense of information, Like we use it every
Well
day
put.
without even realizing it.
Yeah, that's
Mr.
true.
Not
Like
Real Person.
checking the weather forecast or comparing prices online.
Exactly. You don't need to be a math whiz to use statistics.
Okay, that's reassuring. So myth number 9 is data needs to be normally distributed.
Okay,
Now,
I'm going to treat
that
this.
one sounds a little intimidating.
It sounds complicated, yeah, but it's basically about the shape of the data, like how it's distributed. You've probably seen that bell curve, right? The normal distribution.
Right.
So some statistical tests work best when the data looks like that bell curve. But, and this is important, not all data does.
So what do you do then?
You adapt. There are tons
All right.
of statistical methods for data that doesn't fit that normal distribution.
Yeah.
Like imagine you're tracking website traffic, right?
Yeah,
Okay,
yeah.
sure.
Some days are going to be busier than others. It's not always going to be a perfect bell curve.
Right.
But you can still learn a ton from that data, even if it's not normally distributed.
And some of those tests are parametric and some of them are not parametric. Even parametric ones don't necessarily need to be normally distributed. They didn't super get it, but one other point here is that the larger the sample size, the less even tests like ANOVA or even t-test care about their normality. So, get a high enough sample size and it almost starts to not matter.
You just have to use the right tools.
That makes sense. All right, now for a myth that's practically a business mantra, the 80-20 rule always adds up to 100.
That's not a business.
Yes.
That's
The
not
Pareto principle.
That's not
Classic.
So what's
how
the problem
I
with this one?
phrase that
Well,
complaint.
the 80-20 rule, it's about proportions within a specific system. Not like a universal law where everything adds up to 100%.
Okay, I think I see what you mean.
Like, let's say 80% of your complaints come from 20% of your customers.
Right.
Yeah.
That's useful information, right?
Right.
But it doesn't automatically mean that the other 80% of your customers are happy, just that maybe they're not complaining as loudly.
So, they're grabbing pretty stock responses or explanations, which, is totally fine. But these are sort of like the standards of explaining these things. And, the complaints one is definitely right there. I use it sometimes. But the sort of the introduction of it being a business mantra or something, that's not fair characterization. It is though that people will naturally sort of start adding the two numbers together, even though the intent is not about adding.
Interesting. So you need to dig deeper than just that 80-20 split.
Exactly. Now, let's get a little technical for a minute. Myth number 7. The R-squared value needs to be above 0.8 for there to be a relationship between variables.
Okay, I'll admit, I've definitely stumbled over R-squared before.
It's basically a measure of how well your data fits a certain model.
Yeah.
A higher R-squared generally means a stronger relationship.
Right.
But here's the thing. A high R-squared doesn't automatically mean the relationship is meaningful. Like, you could find a high correlation between ice cream sales and shark attacks.
Because it's summer.
Okay, yeah. So because it's summer, you just heard her say. So that's the correlation is not causation thing, and again, a very standard narrative, and that's a myth I didn't even go into. Right, correlation is not causation, but that's not what the R-squared value point was about. You may have learned that hey, you need to have 80% to have it be a good relationship, and that's just not the case. Another way to look at it is how much of the variation are you not explaining with a model, right? So if you have a 0.8 r squared, then there's 20% of the variation that's just sort of random variation or common cause variation. And that might just be what it is, right? It might be 30, 40%. right? And so if there's just like 40% common cause variation that you're just never going to rid of, then you're going to max out at 60% R squared. That's just how it goes. That doesn't mean it's a bad model. It just means that's, how much of the variation you're explaining with the model.
Exactly. Doesn't mean ice cream causes shark attacks, right?
Right.
And on the flip side, a lower R squared doesn't mean there's nothing interesting going on. It might just be a more complex relationship, or you might need more data.
So context is key with R squared.
Always.
With all stats.
Ready for a myth
Context
that
is
seems
key.
a little counterintuitive.
Hit me.
Myth number 6. We can statistically prove things are the same.
Can we, though? That feels off.
It is. See, statistical tests, they're designed to find differences, not to prove that things are exactly the same.
Yeah.
Just because I haven't found my keys doesn't mean they're not out there somewhere.
Perfect analogy. Absence of evidence is not evidence of absence.
Okay, this one I'm a little
I
embarrassed
love that turn
about.
of phrase. There's some borderline mansplaining going on here, though, which is an issue in that the male character is explaining everything to the female character. Again, not real people, but and maybe this is, artificial intelligence. It's a reflection of the real world. There's lots of mansplaining going on out there. I would have wished for otherwise here, but maybe it's just coincidence. I don't know.
It's okay to remove outliers from our data. I've definitely been tempted to do that.
Oh, we've all been there. Those outliers, those data points that are way off from the rest, they can be tempting to just toss outright.
Yeah, they can really mess with your averages.
Right. But they can also be incredibly valuable.
Yes.
They might highlight a data entry error.
Yes.
Or even more interestingly, they might point to some unusual trend or behavior.
Okay, so don't just delete them with...
Okay, so nailed it both. Wow. Okay. It might be data entry error, right? Or it might actually be a real effect. I love that they hit sort of both avenues there.
Without a second thought.
Exactly. Sometimes those outliers are the most interesting pieces of the puzzle.
True.
All right. Myth number 4 is a big one, especially in the business world. Design of experiments, or DOE, will make projects take longer.
I've definitely heard that one. But something tells me it's not that simple.
You're right. When it's done well, DOE can actually make projects faster and more efficient. Instead of tweaking one thing at a time, you're strategically testing multiple factors at once.
So you're getting to the answer quicker.
Exactly.
Nailed it. Wow, this is good. Okay.
Think of it like cooking. You know,
Yeah.
you wouldn't just test each ingredient and recipe one by one.
You'd never finish the dish.
Right. You'd combine ingredients strategically to create the perfect.
Wait, what?
Think of it like cooking. You know,
Yeah.
you wouldn't just test each ingredient and recipe one by one.
You'd never finish the dish.
Right.
You'd never finish the diss? Obviously she's saying dish, but it was very much dis. Wait, so was it dis? Yeah, D-I-S-H. So not pronouncing the sh, but that's hilarious. But, otherwise, what they're saying is that design of experiments is about putting people down. But it's not. DOE is about lifting people up.
You'd combine ingredients strategically to create the perfect flavor profile. DOE is similar. It helps you find the winning combination of factors more efficiently.
I like that. Okay, myth
Alrighty.
number 3 is one I hear all the time. A sample size of 30 has any statistical meaning whatsoever.
All right.
What's the deal with that magic number?
Yeah, what's the deal with
Oh,
that?
the magic 30. Yeah, that's a dangerous oversimplification.
So it's not really a magic number.
Not at all. The ideal sample size depends on so many things. What are you studying? How much precision do you need? What's the population you're looking at? 30 people might be enough to get a sense of favorite pizza toppings.
So good. So good.
So it's not really a magic number.
Back it up.
Not at all.
Not
The
at all.
ideal sample size depends on so many things. What are you studying? How much precision do you need? What's the population you're looking at? 30 people might be enough to get a sense of favorite pizza toppings.
But not enough for,
So might
say,
29.
a medical trial.
Exactly.
Makes sense? Okay, on to myth number 2. We should only test
that was
one
excellent.
factor
That
at
was
a
so
time
excellent.
in experiments. So no more ABC testing all at once.
That's so fast. While it seems simpler to just change one thing at a time, Testing multiple factors together can often give you more realistic and insightful results.
How so?
Well, sometimes factors can interact with each other in ways you wouldn't expect.
Like synergy.
Okay, lots going on here. She said no more ABC testing, which is awesome. Well, online testing calls DOE's multivariate testing, MVT, right? So we're just talking about multiple factors regardless. And they'll talk about having an A and a B and a C as if that were multivariate testing, but it's not, or DOE, right? It's just, that's three levels of the same factor, right? So if you had a blue button, a green button, and a red button, that would be your ABC testing. But that's just three different levels of the same factor. It's not multiple factors. And they nailed that. That was excellent.
Experiments. So no more ABC testing all at once.
That's so fast. While it seems simpler to just change one thing at a time, testing multiple factors together can often give you more realistic and insightful results.
How so?
Well, sometimes factors can interact with each other in ways you wouldn't expect.
Like
Interactions?
synergy.
Yeah, exactly. Like, let's say you're testing different button colors and placements on a website. Testing those separately might not tell you the whole story, but test them together, and you might find that a green button at the top of the page outperforms all other variations.
Because of the combination, not just...
Interesting. So that they used a couple times now going directly to online experimentation. I bet you that online experimentation is disproportionately discussed online, right? Versus physical product experimentation is probably less so, proportionally less so. So it's interesting. That's sort of the representation we're getting from the generative AI.
Them together, and you might find that a green button at the top of the page outperforms all other variations.
Because of the combination, not just one factor alone.
Exactly.
I think they got interaction and efficiency in there, right? But those are the two big, advantages of doing the multiple factors at a time.
Might be the most misunderstood. A low p-value automatically means statistical significance. This one's a biggie.
I've definitely fallen into that trap before, so what's the real story?
Okay.
Think of the p-value like a
This is a
smoke alarm. All right?
This is a
The
hard
low
one.
p-value, it's like the alarm going off. It's telling you to pay attention, that maybe something interesting is happening.
But it doesn't necessarily mean there's a fire.
Exactly. You need more information. You need to look at the whole picture, the study design, the effect size, potential biases. Don't just assume that because the p-value is low, you've made a groundbreaking discovery.
So it's just one piece of the puzzle.
Right. Don't get me wrong, p-values are important, but they're not the be-all and end-all.
So what have we learned today?
Okay, so the way they started out generally talking about the p-value, it left the door open to nail it, but then they didn't quite nail it. They ended up doing this sort of one piece of the puzzle thing, which is also true, but just from a statistical meaning point of view, low p-value does not perfectly mean statistically significant. You need a comparison for the p-value. People just say, oh, it's less than 0.05, so therefore that's that rule of thumb, but that's not statistically what's true. That's not statistically what's happening. So almost nailed it. That was going to be a really tough one.
Right. Don't get me wrong, p-values are important, but they're not the be-all and end-all.
So what have we learned today? Don't blindly follow the statistical rules of thumb.
Right. Statistics is a powerful tool,
Yeah.
but like any tool, you have to know how to use it. Don't be afraid to ask questions, think critically, and remember, context is king.
And on that note, here's a little challenge for you.
Okay, that was the context is king and think critically. Yeah, a lot of people try to do statistics or experimentation like, by rote, by procedure, by pattern, and not like it's all about thinking critically, right? Having the situational awareness, super important point. They hit some awesome points.
Don't be afraid to ask questions, think critically, and remember, context is king.
Yeah,
And on that note, here's a little challenge for you. The next time you see a statistic that seems too good to be true, take a closer look. Could there be something else going on behind those numbers? Until next time, happy analyzing.
Okay, so there were a couple of weird oddities, like that very last thing was a bit of an oddity. We're talking about inferential statistics here for most of this, but there were a couple of inserts of talking about descriptive statistics, right? Like if you see a stat, you see a stat that's likely a descriptive statistic. I'm actually going to run this through a couple more times to see if every time it ends up being the male explaining to the female, but that's sort of a meta thing. I mean, a potentially disturbing meta thing, but a meta thing nonetheless. And I think if I remember, the p-value was a little bit off. The 80-20, not so much did they nail that. But a lot of the other ones, like the 8 other ones, they either did an average or a superb job of talking through these two not real people. So there you go. That was my video, my less than 1 minute video, run through Notebook LM by Google. And, it created an interesting little podcast type thing. So there you go.